Hi, this is week 29 of AP Physics and we're working through Unit 8, which deals with electric force and electric charge. For our agenda, we'll be looking at Coulombs Law as well as the superposition principle. For our lesson objective, it states that students will combine Coulombs Law and the superposition principle to find the net force experienced by a charge. So let's begin with the superposition principle. Here it states that when a number of separate charges act on the charge of interest, that's the one you're looking for, each exerts an electric force. These electric forces can be computed separately. So we can solve for each one individually. Then we add them together as vectors. That is the superposition principle, and we will be using that to solve some problems today. Now let's go ahead and take a look at some examples. In example 2, we're asked the following question. 3 charges lie along the x-axis, seen in this figure. Here we have it. Here's the picture for it as well. The positive charge Q1 has a charge of 15 microcoulombs, and here I have it on my diagram as 15 times 10 to the negative 6 coulombs. And it's at a distance of 2 meters from the origin. So here's the origin, and our Q1 is 2 meters away from the origin to the right. And the positive charge 6 microcoulombs, which is Q2, is at the origin. So here I have it 6 times 10 to the negative 6 coulombs. Now, where must a negative charge Q3 be placed on the x-axis so that the resultant electric force on it is 0? So here's our Q3, it's negative. Both Q1 and Q2 are positive, so it's being pulled towards the left and towards the right. So where must we put that negative charge so that you have equal pull from either side? Alright, so that is the question we're trying to answer. So essentially, how far from the origin? So we're looking for x. Now, well, I know the distance between Q1 and Q2 is 2 meters. Alright, so if we don't know this distance from Q2 to Q3, we're going to call it x. But we also know that, well, therefore from Q3 to Q1 must be 2 minus x, since that is 2. And if we take away the x, that will be 2 minus x. Alright, so that's the distance between 2 and 3 and 3 and 1. Alright, so we also know that the force must be equal to each other in magnitude. So force between 2 and 3 must be equal to the force between 1 and 3. Alright, so that way this negative charge doesn't go towards the left or towards the right. They have equal force on each other, opposite in direction but equal force in magnitude. Alright, so formula for force, that's going to go ahead and be Coulombs Law. So we're going to go ahead and substitute that in for each one of these. So force is equal to the constant, Coulomb's constant, multiplied times the charge of 2 times 3 divided by the distance in between them. So this distance between them is going to be x, and we're going to go ahead and square that. On the other side, it's going to be what's the force between Q3 and Q1? So it's going to be, again, Coulomb's constant multiplied times the charge of Q1 times the charge of Q3 over the distance between them, which is 2 minus x, and that is squared. Alright, so now there's a formula. There's a couple of things you can go ahead and cancel out just to simplify this formula a little bit. If you notice on both sides we have the constant for Coulomb's constant, so it's the same on both sides, so we can go ahead and cancel that out. That's gone. What else is the same? The charge for Q3 is the same. We never have the value for it, but we don't need it because it ends up canceling out. So now we have the formula as you see it now. Alright, we can go ahead and start plugging in values, and again our goal is to solve for x. How far from the origin is Q3? So let's plug in the values for Q2. That's going to be 6 times 10 to the negative 6 x squared is equal to, over here we have 15 times 10 to the negative 6 over 2 minus x squared. Alright, so at this point what we're going to do, we're going to go ahead and do a little bit of cross multiplication and just begin to simplify this problem a little bit. Alright, so I'm going to end up with 15 times 10 to the negative 6 multiplied times x squared. So cross multiply here. I'm going to do the same on the other side. Cross multiply 6 times 10 to the negative 6 multiplied times 2 minus x squared. Alright, what happens now? Let's keep on simplifying. Again, we're solving for x. So we're going to keep on simplifying until we have our x. So I'm going to divide both sides by 6 times 10 to the negative 6, just to simplify. And that's going to give me 2.5 x squared equals, and this cancels out. Now is a good time to go ahead and square the 2 minus x. So once we do that, it's really 2 minus x times 2 minus x. So it's going to go ahead and give me 4, and that is 4x plus x squared. So that's what we have. Alright, at this point, let's go ahead and combine like terms. So we're going to go ahead and move over everything on this side to that side. So I'm going to go ahead, and that's a negative, so that's a positive, so I'm going to subtract x from both sides. So it gives me 1.5 x squared. Then the 4x is going to become plus 4x minus 4 equals 0. Alright, so at this point, we have this set up. What are we going to do now? Well, we're going to go ahead and put it into quadratic formula to go ahead and solve for what is the value for for x. That's what we're solving for. Alright, so let's go ahead and do that. So our formula is this. 1.5x squared plus 4x minus 4 equals 0. So that's a, b, and c, which will go into our quadratic formula here to solve for x. So let's go ahead and substitute the values in and begin to solve. So b is negative 4 plus minus square root of b squared. So that's going to be 4 squared minus 4 ac. A is 1.5 multiplied times c, which is negative 4. And all of this will be divided by 2 times a, which is 1.5. Alright, so next we go ahead and get our calculator, and we begin plugging in these values. That's 1.5 right there. Alright, so it's going to go ahead and look like this. 4 plus minus, and we're going to have 16 minus, oh, that's going to be positive because of that negative right there from the 4. So it's going to be 4 times 1.5 gives me 24. Square root of that divided by 3. Alright, so on this side, let's see, you got 24 plus 16 is 40. Square root of 40 gives me 6.3. So I have x equals negative 4 plus minus 6.3 over 3. Alright, so now we're going to go ahead and solve. One's for positive, one's for negative, and we get our answer for what is x. Alright, if we add them up, it's going to be 6.3 minus 4 divided by 3 gives us a value of 0.77. Alright, but if we subtract, it's going to go ahead and give us 6.3 minus 4 divided by 3 gives us a value of negative 3.43. Only one of these two is correct. This will be the correct answer since our x has to be smaller than 2. So therefore this answer is wrong. So that is our value in meters for x. X is a 0.77 meters away from the origin. And that's the answer for example 2. In problem 3, we're asked the following question. If Q1 has the same magnitude as before but negative, so now we're going to change it from positive to negative. So that is a negative now. In what region along the x-axis would it be possible for the net force for Q3 to be 0? One more time. Alright, and our options are for A, to the left side, which is less than, x is less than 0. So to the left side. Is it between 0 and 2? That's letter B. Or letter C, is it to the greater than 2? Where could we have Q to have a net force of 0? One more time. Alright, so let's go through these guys. Alright, so let's start from right to left. Alright, so for this one, is this possible? Notice that these two are negative, they repel. And these two will attract. But notice the magnitude of Q1 is so much bigger than Q2. And on top of that, the distance is much closer. So that's going to give us a very small force going to the left and a very large force going to the right. So this will probably end up with the charge going to the right, and it would never achieve some type of equilibrium between the forces. So that's not the answer. Here, again, we have a negative and a negative, so they're going to repel, and a positive and a negative, so they're going to attract. So again, notice they're not balanced again, so it's going to move towards the left until it reaches a charge, so that's not it either. Here we have a force of attraction here, and they're close to each other. Here, they're further away, but it's a bigger charge, and they're repelling. So although they're further away, it is a larger charge when compared to the 6, so probably is likely that, yeah, you can find a balance here to the left. So the answer would be A, which would be to the left of the origin, so x equals less than 0. Up next for us is problem number 4. Here we ask the following question. 3 charges lie along the x-axis. A positive charge of q equals 1 is 10 microcoulombs, is at a distance of 1 meter from the origin, and the negative charge of q equals 2 is a negative 2 microcoulombs is at the origin. Where must a positive charge q3 must be placed on the x-axis so that the resultant force is 0? Alright, so we need to balance out the force exerted from q1 and q2 on q3. So where should q3 be? Well, it is to the left of the origin. Alright, now question as soon as come up is, how do we know it's there? Why not put it here? Alright, well, if you look at how the charges would behave, negative and a positive, there'll be a force to the left there. And here, a positive and a positive will be a repulsive force, so another force to the left. So could they balance each other out? No, they cannot. So that's why it could not be there in between the 2 charges. What about to the right? These 2 repel, so forces to the right, but these 2 attract. Couldn't our charge be here? The answer is it could be there, but it cannot, because the charge of q1 is so much larger than the charge of q2. So therefore it's got a much larger repulsive force. On top of that, they're closer to each other, even increasing the repulsive force a lot more, whereas q2 is further away and it has a smaller charge, so that attractive force is very small, so therefore it won't balance out. In fact, the charge will probably just fly off and keep on going. So that's why it could not be here. But could q3 be here? There's an attractive force, and so it's pulling it to the right between q3 and q2, and a repulsive force between q1 and q3. Now, although this q1 is larger than q2, it is further away, so they end up balancing out, giving us a position for q3 there. Now we know why it's there. We can go ahead and start working on solving this problem. Now we know that these 2 forces, they're opposite, but they got to cancel out because there's got to be a 0, no movement on q3. So therefore we're going to go ahead and say, well, the force between q2 and 3 minus the force of 1 and 3 is equal to 0. They got to balance each other out. One's positive is going to the right, the other one's negative. Force of 1 and 3 is going to the left. So I'm going to go ahead and move it over on this side so we can have the following. So they're equal to each other in magnitude. That's why our net force is 0. Alright, so now we've got that part sorted out. Let's go ahead and plug in all the values for Coulombs law. For Coulombs law, it's going to be the constant multiplied times q2 times q3 over what's the distance between 2 and 3 is x, and that is squared. On the other side, it's going to be for f1 and 3, between 1 and 3 is going to be qc multiplied times q1 times q3 over, it's going to be 1 plus the x. So I'm going to put x plus 1, and that is going to be squared. Alright, so that is our setup. Now, as you look from left to right, there are some things you can go ahead and get rid of to simplify this. Notice that the constant is the same on either side, so we can get rid of that. And q3 as well. We don't need the charge of q3 to figure this problem out, to figure out what is x. So that is gone as well. So we're left with just this. q2 over x squared is equal to q1 over x plus 1 squared. Alright, so that is our problem so far. Alright, now what we're going to go to do is plug in the values for q1 and q3 in here and go ahead and set it up. We will need quadratic formula to solve for this problem, but let's go ahead and just plug in all of our values that we got. Alright, so for q2 we got our value is negative 2 times 10 to the negative 6 in coulombs. But I do want to point out that in Coulombs law, you put the absolute value. So that negative, I'm going to drop it because, like I said, Coulombs law, you got to put absolute value. So it's going to go to be 2 times 10 to negative 6 over x squared is equal to Q1, which is 10 times 10 to negative 6 over x plus 1 squared. All right, so that's going to go ahead and be our setup for this problem. I'm going to go ahead and do some cross multiplication. So I'm going to end up with this. 10 times 10 to the negative 6 x squared, after I cross multiply there, will give me 2 times 10 to the negative 6 x plus 1 squared. All right, that's my cross multiplication. I want to go ahead and simplify this as much as possible. So I'm going to divide both sides by 2 times 10 to the negative 6. And after I do that, I can simplify it a little bit further. So that cancels out, and that's going to give me 5 times 10, 5x squared. And on the other side, I'm just going to go ahead and take care of this. X plus 1 squared will give me x squared plus 2x plus 1. All right, so those are our values so far. Again, we're going to keep on multiplying so we can set it up for quadratic formula. So I'm going to go ahead and move the x over here. Notice it's a positive, so I'm going to subtract. So it's going to go ahead and give me 4x squared minus 2x minus 1 gives me 0. So there's my A, B, and C for quadratic formula. Next, we plug all of these values into quadratic formula. So here's our setup for quadratic formula. There we have it. Our setup is A is 4, B is negative 2, C is negative 1. We're going to go ahead and plug all of those into quadratic formula to go ahead and solve for the answer. So we're going to have x equals B negative, which is B is negative 2, so it's going to be negative, and negative goes up positive 2, plus minus square root of B, which is 2, negative 2 squared, it will be positive 4. There's going to be minus 4 times A, which is a 4, times negative 1. And all of it is divided by 2A, so it's going to be 2 times 4. Alright, so that is our setup. Now we've got this, let's go ahead and keep on going. So 2 plus minus over 8 on the denominator. And here what do we have? We got 4 plus 4, negative 1, that is a positive 16. So it's going to be 4 plus 16, square root of that. So that gives us 20, so square root of 20 gives us 4.5. We're going to round it off to that. So it's going to be x equals 2 plus minus 4.5 over 8. Alright, so let's figure out the two values for the 8. For the x, it's going to go ahead and be, let's add first 2 plus 4.5 divided by 8 gives us an answer of 0.8 meters. Alright, and if we subtract, it's going to be 2 minus 4.5 divided by 8 will give us negative 3 meters, which is not correct. It's not negative. It is 0.8. That's our distance, so that is our answer. It is 0.8 to the left of the origin. So that's the answer for problem 4. In example 3, we're asked the following question. Consider 3-point charges at the corners of a triangle, as shown in this figure here, where the charges are Q equals 1 is 6 times 10 to the negative 9, Q3 is 5 times 10 to the negative 9, and Q2 is negative 2 times 10 to the negative 9 coulombs. Also given to us is the angle between the length of 4 and 5 meters of 36.9 degrees. In part A, they ask us find the components of the force between Q2 and Q3. In part B, they ask us to find the force between Q1 and Q3. And finally, part C, they said find the resultant force on Q3 in terms of components and also in terms of magnitude and direction. Alright, so that's all the work we have to do. So here's our diagram, and we're going to begin with Q2 and Q3, and what is the force of attraction between them, here represented by this green arrow going to the left. Since they are opposite charges, they attract each other. So now let's go ahead and put it into the formula. We're going to use Coulomb's law to solve for this. So it's going to be the force between 2 and 3 is equal to the constant for Coulomb's law in newtons times meter squared over Coulomb squared, multiply times their charges, and remember use absolute values, so it's going to be 2 times 10 to the negative 9 coulombs, multiply times 5 times 10 to the negative 9 coulombs, all of it divided by the distance between them, which is 4 meters, and that is squared. So now we're going to go ahead and plug that into our calculator to get the answer. So it's going to go ahead and be 9 times 10 to the 9 multiplied times 2 times 10 to the negative 9 multiplied times 5 times 10 to the negative 9, all of it divided by 16. This is an answer of 5.6 times 10 to the negative 9 newtons. Alright, so that is this first force right there going to the left. Next, what is the force between 1 and 3? So represented here by this green arrow pointing up, because notice they're both positive, so they repel each other, so it's going near the top. Alright, so what are we going to do? We're going to use the same between 1 and 3, that is Coulombs Law. So it's going to be 9 times 10 to the 9 newtons times meter square over Coulomb squared. Multiply times their charges, which is 6 times 10 to the negative 9. Multiply times 5 times 10 to the negative 9 coulombs. All divided by the distance between them. They're 5 meters apart. So it's going to be 5 meters squared. Alright, so our answer is going to be as follows. It's going to go ahead and be 9 times 10 to the 9 times 6 times 10 to the negative 9 multiplied times 5 times 10 to the negative 9 divided by 25, which is 5 squared, gives us our answer. It is 1.1 times 10 to the negative 8 newtons. Alright, so we can compare them a little bit better. I can also move that over and make it 11 times 10 to the negative 9, but we're just going to go ahead and leave it as such. Alright, so now that we have this, we can go ahead and now make vector diagrams. And here's the plan. I'm going to break down this diagonal arrow into its components. That's going to be my next section. Break it down into its components, and then I'm going to find the net force on the x-axis, and then put them both together to go ahead and find part C, which is the force on Q3. Next for us, we're going to go ahead and get this force between 1 and 3, which is 11 times 10 to the negative 9 newtons, and we're going to break it down into its components. So we're going to break it down to the x and y component for that force between charge 1 and charge 3. So I need the force for 1 and 3 on the x-axis and force between 1 and 3 on the y-axis. So I'm breaking down that force right there. We do have the angle that was given to us in the problem, which is 36.9 degrees. And I'm going to go ahead and let's start with the force between 1 and 3 on the x-axis after you break it down into its components. Alright, so notice how this force on the x-axis is adjacent to the angle. So, and we have the hypotenuse. So to solve for that, because they're adjacent, it's going to be cosine. We're going to use cosine for this. So it's going to be force between 1 and 3 on the x-axis is equal to the hypotenuse multiplied times cosine of the angle, which is 36.9. So that gives us an answer of the following. That's going to go ahead and be cosine of 36.9 multiplied times 11 times 10 to the negative 9 gives me 8.8 times 10 to the negative 9 newtons. So that is the force between 1 and 3 on the x-axis. Force between 1 and 3 on the y-axis is going to be very similar, but y is opposite the angle, so that's going to be sine of 36.9. So it's going to give us the following answer. So sine of 36.9 multiplied times 11 times 10 to the negative 9 gives us an answer of 6.6 times 10 to the negative 9 newtons. Alright, so now we have that. Now we're going to go ahead and bring into the fold the following. We have this arrow right here, which is the force of attraction between 2 and 3. I'm going to change the color so that it can stand out to red. And the value for that is 5.6 times 10 to the negative 9. And where would that be in this diagram? It would be right here. It is 5.6 times 10 to the negative 9. So on the x-axis, what is the net force? Well, we're going to go to subtract this minus this. And that's going to go ahead and give us our value for the net force on the x-axis. Alright, so what is that? So it's going to go ahead and be force net on the x-axis is, this is to the left, so I'm going to put negative 5.6 times 10 to the negative 9. And force between 1 and 3 on the x-axis is to the right, so I'm going to put plus. It's going to be 8.8 times 10 to the negative 9. So I'm going to go ahead and plug it into the calculator and see what we get. 5.6 times 10 to the negative 9 negative plus 8.8 times 10 to the negative 9. It gives us 3.2 times 10 to the negative 9. That is our net force. Should have drawn this arrow a little bit smaller, so smaller vector. 5.6 compared to 8.8. So our net force on the x-axis is going to go ahead and be 3.2. And notice it's positive, so it's going to be to the right. 3.2 times 10 to the negative 9 newtons. Now, what is our net force on the y-axis? There's only one force on the y-axis, which is force between 1 and 3 on the y-axis. It is 6.6 times 10 to the negative 9. So that should be roughly about twice the length of this. All right, and should I put it there? No. Remember, when you draw a vector diagram, you go ahead and arrowhead will be where the next arrow would begin. So I should actually put it here. All right, and again, the value for that is 6.6 times 10 to the negative 9 coulombs. So this is what we're looking for, that right there. What is the magnitude of that force? So we're going to go ahead and use some simple Pythagorean theorem to solve for that. So for part C, what is the net force acting on the charge, which is Q3? So we're going to use Pythagorean theorem. So it's going to be 3.2 times 10 to the negative 9 squared plus 6.6 times 10 to the negative 9 squared. And then we're going to go ahead and square root it. So it's going to give us a value of 7.3 times 10 to the negative 9 newtons. And that is the answer as far as when they ask you to find the resultant force. That is our resultant force acting on Q3. All right, 7.3 times 10 to the negative 9. Second part of that, they also want the direction. All right, so we need to figure out this angle right there. So we can go ahead and use sine. So I'm going to put 6.6 times 10 to the negative 9. So opposite over the hypotenuse. So divided by 7.3 times 10 to the negative 9 will give me 0.9. Now, my answer for that, I'm going to go ahead and use inverse sine. That's going to give us an angle of 65 degrees. And that is its direction. So magnitude 7.3 times 10 to the negative 9 and 65 degrees above the x-axis. All right, that takes care of example 3. Up next is problem 5. Here we ask, without actually calculating the electric force on Q2, determine the quadrant in which the electric force vector points. So let's take a look at Q2. Here, left and right, we have positive and negative. So therefore, Q2 is going to be pulled towards the right. And let's check out these two. That's negative, that's positive. So again, there's an attractive force. They're going to be pulled towards the bottom. So therefore, if Q2 is getting pulled towards the right or towards the bottom, the general direction is going to be in this area right here. So which quadrant is it? Here's quadrant 1, 2, 3, and 4. So the answer will be quadrant 4. That's the general direction for Q2. Our last problem is problem number 6. And in it, it states that using the same triangle as before, find the vector components of the electric force on Q1 and the vector's magnitude and direction. So we're looking at Q1, what it does. And notice between Q2 and Q1, it's a positive and a negative. So there's going to be an attractive force in between them, here represented by a green arrow. But for Q1 and Q3, it's going to be positive and a positive, so they repel each other. So it's going to be a repelling force in this direction. And now we know the answer for that. What is the value of that force? Between 1 and 3, 11 times 10 to the negative 9 coulombs, which we had solved for it previously in the other problem. So now, let's go ahead and figure out how we're going to solve this. So we're going to do much of the same. We're going to break this arrow down into its components and then find the net force between the here and the y-axis, and then put them together to get a vector diagram to get our answer. All right, so let's go ahead and first of all get this force for this green arrow force between 1 and 3. So let's go ahead and do that. So force between 1 and 3 is equal to Coulombs Law. So the constant is 9 times 10 to the 9 newtons times meter squared over Coulomb squared. multiply times their charges, 6 times 10 to the negative 9, multiply times 2 times 10 to the negative 9. And remember, you use absolute value, that's why I just put 2 rather than a negative 2. All of it divided by the distance between them, which is 3 meters. And that is going to be squared. So therefore, the force between 1 and 3 is as follows. 9 times 10 to the 9 times 6 times 10 to the negative 9 times 2 times 10 to the negative 9 divided by 3 squared is 9. This gives us 1.2 times 10 to the negative 8 newtons. Or I'm going to put in the same value so that they'll look the same. It's going to be 12 times 10 to the negative 9 newtons. Alright, so that is the value for this green arrow going up. That is between 1 and 2. Up next, let's go ahead and figure out what will be our net force. So let me write down what we've got so far. And for this one, right over to the side between 1 and 2 is equal to 1.12 times 10, 12 times 10 to the negative 9 coulombs. So there we have it. Alright, I'm going to go ahead and erase here for more space. Now, let's break this one down into its components. So we have that green arrow going diagonally. Let's break it down into components. So first of all, we're going to need that angle. So this angle right here is actually easy to get because it's a 3, 4, 5 triangle. We know that it's a right triangle. So if that's 90 degrees and that's 36, we can go ahead and figure out. So it's going to be 180 minus 90 minus 36.9 gives us 53.1 degrees. Alright, so that is that angle there. Alright, so therefore, over on this side, that's going to be a congruent angle, same angle as well. So now, let me go ahead and zoom in on that section a bit and redraw it. So here we have our green arrow, and it has a value of 11 times 10 to the negative 9 coulombs. Right? We know what that is, and we're looking at that arrow. And now, going straight down, I'm going to put its components. So its components is going to be going straight down there, and it's a right triangle. And we know this angle to be 53.1 degrees. Alright, so that's what we got so far. So this is my force between 1 and 3. So now I need my force between 1 and 3 on the y-axis as well. Force between 1 and 3 on the y-axis, and force between 1 and 3 on the x-axis as well. Alright, so we're going to go ahead and solve for both of them. And for that, we're going to go ahead and use our calculator. And let's start with the y-axis. See, the y-axis is adjacent to the angle, so we're going to use cosine. So the answer is really 11 times 10 to the negative 9 times cosine of 53.1 degrees. Alright, so our answer becomes cosine of 53.1 times 11 times 10 to the negative 9, 6.6 times 10 to the negative 9 newtons. Alright, for force on the x-axis is going to go ahead and be 11 times 10 to the negative 9 times sine, and I'm using sine because it's opposite the angle. So that's going to go ahead and give us the following answer. So sine of 53.1 is going to go ahead and give us 0.799 multiplied times 11 times 10 to the negative 9 gives us an answer of, we're going to round it off to 8.8 times 10 to the negative 9, and that is on the x-axis going in that direction. Alright, so now we're going to put two things together. Notice this on the y-axis and this arrow going up in the y-axis as well. Well, we need to find what is the net force on the y-axis. Alright, so this was going up, so I'm going to go ahead and label it as positive. So my force on the y-axis, my net force, I should write. My net force on the y-axis is going to be 12 times 10 to the negative 9 minus 6.6 times 10 to the negative 9. So that gives us the following answer. (5.4) times 10 to the negative 9. Notice it's positive, so therefore it's going up. So I'm going to draw a vector arrow with an arrow the net force going up, and it has a value of 5.4 times 10 to the negative 9 coulombs. Sorry, not coulombs, newtons. Next, what about my x-axis? What's the force on the x-axis? All right, well, that's the only force on the x-axis is this one, so therefore that's my net force. And I'm going to go ahead and add to my vector diagram. And again, from the arrowhead, that's where you have the next one, and it is 8.8 times 10 to the negative 9. To draw up to scale, I'm going to have to shorten that, newtons. So it's going to go ahead and have to be, that's what we're solving for, the magnitude, that's a right triangle. So here we have our net force on the y-axis, here's our force on the x-axis, we got it from right there. And now we use some Pythagorean theorem to solve for the hypotenuse there. And let's go ahead and do that, and that's going to go ahead and be our magnitude. So it's going to be 8.8 times 10 to the negative 9 squared plus 5.4 times 10 to the negative 9 squared. And the square root of that answer is going to go ahead and give us 10.3 times 10 to the negative 9 newtons. And that would be our hypotenuse right there. So that is the magnitude of the force going that direction, since it is going up and to the side, it ends up going slightly that way. All right, at what angle is that right there? All right, so this angle right there, I want to go ahead and use opposite over hypotenuse to get the angle and inverse sine of it. So 8.8 times 10 to the negative 9 divided by 10.3 times 10 to the negative 9 gives us 0.85, and inverse sine of that is going to give us 58.7. So the angle right here is going to go ahead and be 58.7. Let me change the color for this angle right there. So 58.7 from the y-axis to the left of the y-axis. All right, that takes care of problem number 6. This brings us to the end of this video. Also brings us to the end of Unit 8. Thank you so much for watching.